Hello, everyone. Thank you for coming to VCS group seminars. Today, we have Christoph Hirche that is going to tell us about quantum differential privacy and information theory perspective. Thank you.
Thanks a lot. So I'm going to talk about quantum differential privacy, and I kind of try to pick this as a topic, as it's somewhat a bit at the intersection, I hope, like information theory, which is more like my traditional field of work, and computer science. And yeah, I think I should start by just giving like some motivational introduction into the main topic of this talk. And so first I'm going to discuss just in simple words like what differential privacy actually is. And the main idea here is actually quite simple. So let's say it's like a common problem that nowadays every company and so on, they're gathering big amounts of data about every single user of their website and so on and so on. And often these data sets, they're in some way processed. Like, I don't know, let's say there's a database of medical statements about all the patients of a hospital or something. Then the hospital might want to publish some statistics about their customers, about their patients. But then, of course, we as the patients, we are in principle fine with publishing some like general statistics, but it's also important to us that somebody who gets these statistics can't actually make any interferences about me personally as one patient in this big group of people. So the goal of differential privacy is kind of to give you a theoretical assurance that if somebody gets the outputs of this algorithm or this, I don't know, this process data, that it should not be possible for that person to make any interference about the individual subject in that database. And how this is usually done is if you have a list of all the patients and the data, if you change the data of one particular individual in the database, the outcome of the algorithm should still be more or less the same. And that ensures that you can't say like what data this one individual contributed to the database. You only get like an overall statistical picture of the data. And for this talk, of course, we want to move from the classical picture to quantum picture. And now the picture becomes way more abstract for now. We simply handle in some kind of inputs, which represent the original like database. So we just have some data that is classified by a set of input states. In particular, like let's say we input a state rho, and the algorithm just is some CPTP map, so any quantum channel. But we still want to maintain like a similar security behavior or safety behavior, in the sense that if I input two states that are neighboring, and a little bit more in a bit what neighboring actually means, then it should still be very hard to distinguish between the outputs of this database, right? Of these inputs. So if you, of course, if all outputs of an algorithm would be hard to distinguish, then your algorithm would be useless, right? Because you couldn't actually make any interference on which like data was used to generate the output. But here we only require these neighboring states to be to lead to basically identical outputs. And so in the first work on like quantum differential privacy, how this was defined is just to take rho and sigma that are close to each other. So you can pick any distance, but the typical thing is to pick the trace distance. So if you have two states that are close in trace distance, then the outputs should be almost indistinguishable. And then there was later work by Scott Harrison and others, which tried to mimic more closely the classical way of defining neighboring. So in the classical case, it's like you have this database and you swap one entry in the database. And neighboring classically usually means two databases are neighboring if they differ in only one entry of the database. And Scott defined the quantum version of neighboring. If we have a multipartite state, then two of them are neighboring if a local quantum channel and only one system can transfer the state from one state to the other. Okay, so this kind of just to say that there are many ways of defining this neighboring framework in the quantum setting. And the important thing is just for now that neighboring defines some kind of closeness in the input space. And for the rest of the talk, I'm mostly going to leave the definition of neighboring open. But when I come to examples and plots and so on, I will use this example of the trace distance as closeness definition.
Oh. So,
yeah.
Input space formally is
yeah.
Is it like from the original motivating example, patient 1, patient 2, patient 3, right? And the data of.
Yeah, you can think of it as like a vector or something, and then you would think of the classic, I guess, the Hamming distance or something. Like if two vectors differ only in one input, like usually it would take like a long binary vector or something, and then if you can get one from the other by just swapping 1, 0 to 1 or something. So Hamming by 1, that's what we usually find.
Right. So let's say that our input space is 0 to 0.
Yeah.
And then the neighboring can be just give 1 meter.
Yeah.
Right?
Yeah.
Now we can also define all distinctions on 0 to 0.
Yeah.
Right? Right? Now probability distribution of course will be arbitrary. Right?
Yeah.
Right. So I'm saying that is already captured in this issue. I mean, you don't have to go on about thing. Even there is an issue. Like, whether you're taking L1
Right,
closeness,
in some sense. Yeah.
whether you're taking L1 closeness, whether you're taking
Yeah.
because it depends on what your domain is. Is your domain
Yeah.
there or is it on the board?
Yeah. I think it's kind of okay. Let me go to like the formal definition of the differential privacy.
Yeah.
Because then we see that
Because in the classical case also, if you take your domain to become distributions, then it is not capturing your patient and data. Because then you
so it's a different setting.
right? So you're playing probability on a particular patient and just keep it very close to it or
Yeah. Then it doesn't really apply to this patient setting.
yeah, it doesn't apply, right? It doesn't stop capturing patient.
Yeah. So, but you can, you kind of just choose your definition of neighboring, whatever is convenient for your particular application. So for the classical setting, usually it's this patient idea that you choose like Hamming distance as neighboring. And then quantum, it's a bit harder to define what is like your actual task that you want to go for and so on. So there's like a host, like a variety of different neighboring definitions. And like I said, most what I'm going to talk about is actually independent of which definition of neighboring you choose. But yeah.
Perhaps only with your states. So, because what matters is we always work with your states.
Yeah, you can do that absolutely as well. Things actually become a bit easier if you restrict yourself. Yeah, exactly.
Essentially, like if you take so the original data is some vector, right? And then you're perturbing the difference. There is a noise vector you're adding, right? But then in the original patient, the noise vector is no. low energy.
Yeah.
So now, yeah, sure. So if that is the kind of noise that, then we can also do that for the differential.
Sure. Yeah, that's actually in practice that's actually done a lot, like how people in classical computer science also look at differential privacies. Often they want algorithms that kind of keep your computational capabilities as preserved as possible while reaching differential privacy. And then the typical thing people do is add like either like Gaussian or Laplacian noise or something, just a little bit of noise to your data set. And that makes it differentially private by achieving this, but it also doesn't hurt your computation too much because it's just like a low level of noise in some way. So in some way, this is exactly what you do in practice. You add a little bit of noise and then you get differential privacy without hurting the data.
And the noise comes from a special setting, like local noise. There is a notion of localization.
Yeah, you can do different things. Like yeah, often it's like, just like yeah, you can do like local Gaussian noise or something on each input. Okay, I think works. And yeah, I come a bit more to the quantum version of it. Like, the difference somewhat is that classically people really see that as an algorithm. They want to add artificial noise to make the algorithms private. And now here in the quantum setting, the viewpoint is somewhat a bit changed because people have quantum computers and stuff that are already noisy. So the argument people are trying to make right now is a bit that you kind of get differential privacy for free just by the noise that inherently is present in the quantum computer. So it's like, kind of like the noise that is usually like an annoyance when you compute anything, kind of like reframe it as something not positive, but like the side benefit of at least giving you privacy in your computations. Okay. Yeah, let me briefly go just through the formal definition of quantum differential privacy as it's usually stated in the literature. That is simply you have a set of quantum states, and now you want that for all measurements and all neighboring, whatever that means, input states, the probability of concluding that one state was present rather than the other doesn't differ too much. Like the probability from, let's say, detecting rho should not be too different from detecting sigma. And of course, just because this has to hold for all rho and sigma that are neighboring, of course, the opposites, like implication also holds that I switch rho and sigma. And you can see these epsilon and delta, they're like two typical error or like approximation parameters. And if I pick them to be very small, then this is extremely restricted. And in fact, for example, and this is going to be an important point later, if we take
when you look at rho sigma, how close was that?
I mean, this just means, yeah, just like they have to be neighboring. And exactly, that could, for example, mean close in trace distance below some constant or something. But for now, this is kind of all the demand. And what was I going to say? Right. So if you pick special examples of these parameters, they can in principle be anything positive, but you see that, for example, if you take epsilon to be 0, then this is a too restrictive condition in the sense of that this actually becomes equal to the trace distance, like a trace distance requirement. And I'll show this in a bit more detail later, but that means that your algorithm will be very severely restricted in like computational sense, because if all these algorithms are close in trace distance, all the outputs, then there's not that much you can actually do with the algorithm. It's just not a great algorithm. And okay, we have these two parameters. It's maybe last thing about this epsilon delta. And the original definition did not include this delta. And the delta is something that people later added to make things a bit easier and so on. But the delta is something you really want to be very small, because it actually allows for all kinds of attacks already classically that usually we want to avoid. And the epsilon, you have a bit more leeway. This is kind of the parameter we are more interested in. The delta is kind of just what you want to keep as small as possible. Okay, and now I want to kind of like how to like frame this a bit more into like an information theoretic way, and not have like this like statements of for all measurements and so on. That's something information theory kind of don't really like that. We just want to work with like things like the trace distance or entropies and things like that. So that's kind of what we're aiming for here now. Yeah, sure. Basically. And that's yeah, the Dmax epsilon is kind of one way of looking at it. So of course you can rewrite this inequality, say this as the whole for all states and all measurements. Then we can rewrite this in this way. And as I mentioned before, if we pick like the special case of epsilon to 0, then we kind of all know that this actually becomes the left-hand side just becomes the trace distance. Okay, and from here, okay, we know the trace distance is really useful and has like lots of good properties. So we kind of just want to go and incorporate this this epsilon further. And it turns out that if you just do that in exactly the same way, this quantity actually becomes what is called the hockey stick divergence. So this is a maybe not as well known divergence that actually is very often used in the classical setting and all kinds of settings, especially even people look at it in like finance applications and so on for some reason. And but there was also recent, well, not that recently, but a couple of years ago, a paper that looked at strong converse bonds in the quantum communication setting, and they introduced this quantum hockey stick divergence. The only kind of simple thing here is that this actually equals this. Yes, yes. And so in that case, we can rephrase very easily the condition of differential privacy as a condition on this hockey stick divergence. I think I write this out more on the next slide, or not quite yet. But okay, the Sharma and Vasi paper, that is the one I just mentioned on the strong converse results on capacities, and they first introduced this this quantum hockey stick divergence. And then we cannot just rewrite this in a slightly different form, but of course this proof is really easy because you just look at the proof of the trace distance at constants at the appropriate places. Right? But what this mostly allows us, apparently I first want to go to some properties. Okay, some properties of this quantity that are going to be useful for working with differential privacy in this formulation. So one, of course, this quantity is closely related to the trace distance. Not just that if we take gamma to the 1, that it's then equal to the trace distance, but we can actually write it also in terms of the trace distance. And an important property that also Sharma and Vasi already proved is that it obeys data processing. So if I apply any quantum channel to the two inputs, then this can only make the quantity smaller. And you can already kind of see how this is going to be useful for differential privacy. That is, whatever noise in some way I add to a set of states or something, that can only make the set more secure. Right? So that's a very simple corollary of this data processing. And then in our paper, we prove a couple of more properties that are all maybe in detail not that important right now. But just kind of bounds, like for example, you can bound it in terms of the fidelity, for example, that is the next equation, in a bound that is tighter than the usual one if you would go through the trace distance. And what maybe is worth pointing out in particularly is the last one, which actually just kind of what you mentioned a minute ago, that you can go from this property to the smooth max relative entropy. So the hockey stick divergence being smaller than epsilon is actually equivalent also to a condition of the smooth max entropy. And I have this exclamation mark next to it, which is kind of, okay, that's maybe just for the people that are actually very familiar with these quantities. But the smoothing here is not the smoothing that is usually used when you look at like information theory papers or something, which is generally a smoothing over states or over subnormalized operators or quantum states. But for some reason here, that doesn't seem to be sufficient. It's not clear if you can maybe make it sufficient. But a priori in this statement, the smoothing is over all operators independent of the normalization. Like they can also have trace larger than 1%. Which kind of makes this quantity a bit different from the one usually used. But it's not clear at the moment whether this is just like a technical artifact of the proof used, or if these are actually different quantities.
Actually, so for now, you're just saying anything epsilon doesn't go.
Yeah. Exactly. Everything in every positive operator in like an epsilon ball around it, but not necessarily subnormalized.
But typically, if you're taking the setting of, are you taking the setting that is loaded as into the epsilon? Okay, so just, I mean, the epsilon there is like I think the law of gamma here.
Yeah, exactly. Gamma just equals epsilon.
Epsilon there. So I'm wondering, but I mean, we want to know epsilon is smaller. Yeah.
But gamma would generally be small.
Like much less than 1. Or
typically, I would say less than 1. Yeah, but epsilon has a wider range. Like, it could even be larger than 1. I would say. Like the delta is the one that you really need to keep like information theoretically small. There you want like something like 10 to the power of -4 or something. But the epsilon you can have a larger range.
So here, if your gamma can be large. This is, I mean, the first one will be everyone is irrelevant. I think the E gamma, if your gamma can be like 1,000. Right?
Yeah. But if your gamma becomes too big, then the
trace of gamma should not be large.
Oh, I see. It should probably be like the positive part of that equation. Of course, epsilon gamma can never be negative. Lower bound. But the gamma itself can be anything larger than 1. So it's like last time was just kind of a correction term. But yeah, the quantity cannot become negative. So I guess it needs to be like a minimum, so maximum of 0 or this equation. But that's actually where the name hockey-stick divergence comes from. If you plot it for fixed states of a gamma, you have the decay until it reaches 0, and then it just stays 0 forever with going gamma. And that's kind of like people thought this looks like a hockey stick, and that's where the name comes from. Classical. Yeah. Okay. But this is kind of just meant as like this is the quantity we're using, and it has like a couple of nice properties, and particularly what you thought in the beginning that you can rewrite this differential privacy as like condition on the smooth max effect. One of these observations. Okay. One tool that we like to use in information theory is subtraction coefficient. So I briefly wanted to introduce this as a tool, and subtraction coefficients are something that is meant to make a more precise statement about this data processing that I mentioned in the last slide. So if I have any kind of like any good divergence or something, any good like a relative entropy or the hockey stick divergence, they obey data processing in the sense that applying a quantum channel only makes the quantity smaller. Okay, and of course, in principle, this is a very vague statement in some sense. So the contraction coefficient tries to quantify by how much this data processing makes the quantity smaller. And this, okay, you can see here, it's defined as a supremum over possible input states. And what it really just tells you is that the data processing inequality that I kind of repeated here now gets this extra coefficient. So if you're able to calculate the contraction coefficient, then you actually know by how much your quantity gets smaller if you apply a certain quantum channel, like A in this sense. Okay, and again, you can probably already see how this is useful for differential privacy, because it can tell you that the channel doesn't just apply like noise, but it also tells you by how much differential privacy you gain by applying a certain quantum channel. If you're just able to calculate this contraction coefficient. Okay, and one last statement about this contraction coefficient is that usually they are actually very hard to compute. So if you look at other divergences, like the relative entropy, for example, computing, like we don't actually have like good ways of efficiently computing these contraction coefficients. And that's mostly because they're like this fraction of the two divergences. And for the hockey stick divergence, we actually found a very easy expression where we don't have like this, fraction of two terms anymore, but we just have to optimize one divergence actually over orthogonal pure state. So opposed to like general contraction coefficients, this particular one is actually rather easy to compute, both numerically but also.
10 years in the
Sorry, yeah, I think I just solved from A to N. But yeah. And so this is like, again, for gamma equals to 1, this reduces to a well-known result for the trace distance, but it's useful in the sense that it really makes things much easier to compute. Okay. So here we have, right, and this is kind of the conclusion that I was given all this while. We can, usually this definition of epsilon delta differential privacy, which for us was always a bit annoying to work with because you have like all this like suprema over measurements and so on, or you have to look at all measurements, actually becomes this kind of like easier form in terms of like a quantity that we as information theory people like, which is like divergences, like max entropies, hockey stick divergence, all this kind of thing. Okay, and now from here we kind of want to see what we can do with this in terms of yeah, like this is actually useful to reformulate this in this way. And of course you get like some known results just as corollaries. And the one I already mentioned is post-processing. So if you have any algorithm and you add more noise to it in the end, then your algorithm just becomes more differentially private, or at least it doesn't lose any differential privacy by adding more steps afterwards. And okay, this of course, like now you say this like obvious result, and in some way it is because it just follows from this data processing property, but it kind of reduces like a half-page proof in the earlier results to like a one-line proof in this changed formulation. And the other one is a parallel composition. That is, if you have two differentially private algorithms and you take like the tensor product of them, then also the tensor product is differentially private. And yeah, and if I want people online to see it, they see my mouse. The crucial point here is that the error terms, the epsilons and deltas here, they kind of just add up if I combine two of these algorithms. And if I have time, I might come back to this point a bit later. And this again is like an easy like two-line proof or something just based on the max relative entropy. And interestingly, okay, this was kind of semi-known before, in the sense of that the first paper that talked about quantum differential privacy actually claimed this, but it turns out their proof was wrong. So in some sense, like this is like the like as far as we know, it's the first like proper proof, and it's like a really simple proof of this statement. Opposed to again, the old proof was like a page long or something. Okay, so these are just like some basic things we can do by just rearranging this as like information theoretic quantities. And now I want to talk a bit more about like particular algorithms that people are generally interested in. And the one thing here I want to talk about first are these kind of like layered algorithms. So here we have different, as you can see, the algorithm is kind of built in these layers. And I alternate what I call like a computational layer. So this is like actual like gates or something you want to do in your circuit. And then I have these layers, these quantum channels N, that are noise layers. And these are the ones that you actually don't want to have usually. That just, I don't know, let's say some depolarizing noise or some Pauli noise or something. That usually just makes your computation harder. And these are actually very commonly used models. Like you can, like I mentioned, kind of like quantum circuits. Of course, this is like the most natural thing to look at it. Like you have your gates, and then the next step is just like noise that is like making your gates somewhat worse. And you have many levels of them, and this appears like in all kinds of like circuits or even like neural networks or some. They're all based on this like layer structure. And one thing you can kind of also get more or less as a result of the previous formulation is that you can now take these layered algorithms and you just like abstract layer by layer the circuit into your differential privacy formalism. And what you do is kind of you just remove all the computational layers. They don't help you achieving differential privacy because they're like guided, like proper some kind of computations you want to do, like which actually give like a computational value. So those you just get rid of by data processing. But then for the noise layers, you use this like proof data processing in some way by keeping track of the contraction coefficients. So what you get kind of as a simple result is that you get the decay of the hockey stick divergence, and you get all these contraction coefficients in between. And it's simple actually if you look at the corollary below, where we assume that all these noise channels in each layer, like each layer by itself is identical. Like let's say every layer can just be local depolarizing noise or something, or a particular local or global, whatever, Pauli noise. And then we just get an exponential decay of the delta parameter in the differential privacy with the length of your circuit N and the base that is given by the contraction coefficient. So if for a particular channel you're able to calculate your contraction coefficient, I argued earlier that this is actually not computationally quite easy to do most of the time. You always get that noise gives you an exponential decay of the delta parameter in the differential privacy, which means that your circuit is just long enough, eventually you always reach differential privacy. Right, exponential for the optimization.
Yeah.
It's
not quite limiting the number of keys.
Yeah, I think it's actually even easier, like, because you just optimize over the like orthogonal pure states or something. I think computation is really not that much. We have mostly looked at cases where you can actually analytically calculate it. Even that usually is not that hard, or like at least to get analytical bounds on the quantity. Yeah, I'll show some examples in the next few slides. But okay, that's kind of like the first corollary is that differential privacy always has this exponential decay. But of course, there's again also this connection to computational resources. So of course, people have looked at like kind of noise thresholds and so on in quantum computation. And if there's too much noise in your circuit, then also your computations become useless. Right? And in principle, this decay is also exponential. And in fact, if you choose the epsilon to be 0 as a special case, you get the trace distance. You kind of recover like the same behavior. You could get the same result also for your computational quality of your circuit. So you also know that if there's too much noise with n, you also have a decay in like an exponential decay in computational quality. And from our results, you can kind of see that differential privacy always decays faster. That means you reach differential privacy earlier than you reach like this computational computational issues. But as you cannot see, like if you have from the picture, if you have many differential decays, exponential decays, there might be a very short time frame where you reach one and then the other one just catches up. So the question is if you can do better than these like kind of obvious bounds or these like exponential decay bounds. And indeed, if you go and you look at particular channels, then you can actually do much better.
But the vertical axis.
The vertical axis is delta. I didn't put it on the slide. So this is a plot for different values of epsilon, and then how the delta decays for like, I don't know, I think I thought it like depolarizing noise. And on the x-axis, you have like the number of layers at n, and you have the delta decay shown on the y-axis. So just to illustrate the exponential decay of the delta for different values of epsilon, showing that epsilon gets larger than your decay also faster. You reach epsilon differential privacy faster if you allow for larger epsilon.
But it's not the way that delta decreases. Isn't that like a fixed? It's like a fixed parameter that you want to achieve.
Sure. Yeah, in some way you're right. Like usually you would say I want an algorithm that is epsilon delta differentially private with like fixed epsilon delta. And this kind of tells you which n you need to reach so I can guarantee you that delta.
Okay.
Yeah.
We're imagining a model where the client sends role to a server. And this is the server that needs to that wants us to believe that they have 8 layers.
Sure. This is based on you knowing that there's a certain amount of noise in the algorithm.
Okay.
There's no like. I guess you can also think about how you certify noise in an algorithm or something. But that is I mean, if you have like, that's like a different question something. But if you have access to your algorithm, you could use like certain like tomography kind of protocols to figure out how much noise is in your algorithm, and then you can say, okay, this amount of noise or this type of noise will guarantee me that much differential privacy. But yeah, the way I discuss it is usually assume that we know the circuit and we know the noise, so we can calculate all these kind of things.
It's like we have to this noise store as an assumption that working people saying that academic only stores distributed with this amount of noise. I think they have also actually
In some way, maybe.
then so we are assuming that they don't have a connection.
Right. So this assumes a circuit where this noise is present.
Okay.
If you get rid of the noise in some way, then of course this doesn't work. But yeah, but it would have to be something particular, right? It could not just be the computational layers themselves. They are included in this algorithm. So it can't just be the computational lower layers that do something smart, but it would really have to be some like external, like extra like error correction. It really gets rid of your noise. As long as the noise is there in these computational layers, this holds. Just like,
So another thing, again, go back to the application, right? So in there, like if epsilon is 1000, I'm just wondering, does it make sense there? Like because you don't want the patient information to be revealed, and you kind of, I mean, I don't know, but you kind of meaning if your epsilon is 1000, then Emacs is like 1000, then you kind of revealing that I don't know, data. What you do is like
yeah. If you want to think about scale or something, I mean, even if you just look at like this hockey stick divergence, the epsilon becomes, I'm sure there's like some easy upper bound or something. Like it must have to do the second state, let's say the second state sigma or something, with the maximum eigenvalue of sigma. Like if gamma becomes larger than the maximum eigenvalue, of rho. So, well, anyway, the fraction or the fraction between the eigenvalues of rho and sigma, they kind of give you an upper bound on what's like the largest gamma that even makes sense. Because after that, the hockey stick divergence is always going to be 0. So you always get like your desired level of differential privacy if you just choose gamma large enough. So a very large epsilon just makes the whole thing trivial. But
I think that what are the kind of epsilon you want to achieve? I mean, like if I say, oh, I have this differential privacy algorithm with a epsilon 1000.
Yeah, I think that is not.
So then the patient will be like, oh, like
yeah. Yeah. No, I think the typical. Kind of guessing, but I think the typical parameters is like area around 1, like an epsilon around 1, maybe something like 1/2, 1 or something. That's like a reasonable epsilon.
If your epsilon is small, let's say 0.1.
Yeah.
Then you do epsilon also. I mean, then you're like one, whatever. You're in 1 plus epsilon. So overall, you can put it in the Amain error extent. Then I don't know why you want to maintain the Amain error separately and let the max error separately. If they both.
No, but you kind of want them to be small. That the epsilon, the multiplicative errors, it can be like this, like order somewhere between 0 and 1. Anything is like still good privacy in some sense. Like maybe you allow like 0.2 or something on epsilon, but that is like this multiplicative error, and that apparently usually it doesn't hurt you too much in your privacy applications. But so
you can allow epsilon to be like 0.2, but delta should be really tiny.
Yeah, delta then should be really tiny. Delta should be like I said, like 10 to the power of -4.
Oh.
That's like really like this information theoretics mode. And I think the reason is that the delta, you can also think of it as like a probabilistic statement. So, okay, that goes a bit beyond what I want to talk about, but the idea is that the delta allows you actually to rewrite this in a way that says differential privacy holds for all except one, like holds with probability 1 minus delta or something on all this possible states or something. And that means there's always like this fraction delta of states where differential privacy might not hold at all, right? And the multiplicative error, it doesn't kind of give you that leeway. There's always like a certain amount of differential privacy on all states, but the additive error means like, I don't know, like 90% of your states are going to be, or database entries are going to be protected, but 10% might be not protected at all. And that's kind of the idea why you want data to be as small as possible, and epsilon, you have like, that's kind of the parameter you can play with. Okay. Where did I want to go next from here? Right. So actually, I don't even know about time or something. I'm running like way out of time to stop.
We have 12 minutes.
I see. Okay. So one thing I want to talk about briefly is, of course, we have this exponential decay, but then if you look at particular noise models, you can actually do way better. And that is again important to differentiate between like this computational problem that the noise forbids any useful computation and differential privacy. And the idea is just, okay, the second line you see, we can easily compute like actually the contraction coefficient, but on the way, you also get a formula that upper bounds any kind of hockey stick divergence for the, let's say here, the depolarizing channel, which I put this on the top, right to see in case you forgot what the depolarizing channel is. And based on these results, we can actually get much better bounds on the data that is achieved, or that we can achieve with depolarizing noise. And okay, maybe I don't want to, in the end, it's really just like calculations. So since it might make more sense to discuss some interesting parts, skip over this a bit in particular, but this framework kind of allows you to give these bounds that give you much better guarantees. In particular, while the previous contraction coefficient bound had this exponential decay, these improved bounds, they actually guarantee you delta after like a small circuit depth, or like delta equal to 0. And that's something you see in the plot on the right of the slide, that these improved bounds, for example, okay, I just picked some value for the depolarizing channel, but there's like the fixed n for which we actually reach delta equal to 0. So we, of course, this is also still a function of epsilon, but for a certain epsilon, we can always reach like perfect epsilon differential privacy, so delta equal to 0, after like a finite depth of depolarizing noise. And then, because I actually wanted to also come to some extensions that we do in this work, I'm going to just briefly skip over some more kind of like corollaries of this, which of course you can also bound epsilon, given that you have like a certain delta that you reach. You can also see what is like the epsilon that you can reach, and this actually reproduces some earlier results where people in particularly focused on depolarizing noise and just did like all the tedious calculations that now kind of with this approach is just much faster. And okay, so we can reproduce these results also. And then of course one thing, and then again skipping over like the calculations and stuff, we can compare local and global depolarizing noise, because that's kind of extends on which what was previously done. That we can also have like these kind of more complicated channels in some way. Like local depolarizing noise is just like a nice, it's like a more practical model, because often if you assume that every gate in the circuit has like its own depolarizing noise or something, which is more practical than one common depolarizing channel that acts on your whole layer. And we can easily we can compare how like local and global and so on affect your circuit differently. And then you can, for example, see that if there's local depolarizing noise in your circuit, and then you want to artificially add noise, which is like usually done in the classical setting, then adding global depolarizing noise makes much more sense than adding local depolarizing noise. But of course, usually you don't want to add noise in your quantum computing. And then, okay, just some brief statement. There was a recent paper by Fazim, Hammes, and Shayegi, where they showed that any non-unitary qubit channel actually has a non-trivial contraction coefficient. And this also helps us, also allows you a statement here for the differential privacy that you have always proper exponential decay for every non-unitary qubit channel. But okay, these are just more examples where you can make use of this framework in a more computational way. And then if I still have a few minutes, I just want to discuss briefly 3 extensions somewhat of this differential privacy setting that are kind of new to the quantum setting. And I think the most interesting one is maybe the second one. So just going to briefly skim over the other 2. And the first one is that there's something in classical information theory that people call local differential privacy. And this kind of just means you don't just check for all neighboring states, but you check for all states. And classically, this is often applied to network settings. So if your database isn't just with one person that can provide them your whole database, but your database is distributed over many people who individually send you data, then they want their own data to be differentially private, handled differentially private. And so a statement over the whole data set kind of isn't sufficient for them. And this is when people look at local differential privacy. And just for example, simple corollary of like technical properties is that if you actually look at differential privacy in this local way with optimization over all states, and actually you can even say over all pure states, for example, or more restricted sets, then actually this also gives you an upper bound on the contraction coefficient for the, so 1, again, remember that 1 means the hockey stick divergence reduces to the trace distance. So you actually get an upper bound on the trace distance contraction coefficient, which means if you have local differential privacy, that will very quickly make all computations useless in the circuit or in your algorithm. Okay? So that's kind of just like a simple corollary if you extend this model. But of course, this might still have applications if you look more particularly at like distributed databases or network settings. Okay. And with that, I want to come to Rényi differential privacy, which is something that in the classical case, classical setting has really found like lots of applications. So I'm kind of hoping that the proper quantum generalization of this will also help like in the quantum computer science to like really get a better handle on differential privacy. And the reason is kind of what we discussed just now, right? That the data parameter is something that you really want to avoid as much as possible. Like in one way it was introduced, so was introduced because just epsilon differential privacy is often too strong of a criteria to actually achieve. But if you introduce the data, you get this fraction of like data % of your states or something that are actually not protected at all. And Rényi differential privacy somewhat aims to provide like a middle ground between these two concepts. And as I said earlier, or as we saw earlier, epsilon differential privacy can be written as criteria on the max relative entropy. And of course, like how would you now go for a Rényi version? Of course, you just replace the max relative entropy by any other Rényi divergence or something, any Rényi relative entropy. And classically, or in the early days of quantum differential privacy, you looked at these measurement approaches. Like you formulated things in terms of measurements. And of course, we can just do the same thing here. Like we could define probability distributions based on the outputs of measurements on the algorithm, and then apply like the classical Rényi divergence to that. Right? This would kind of mirror the original approach. But it turns out that this would just become what we call the measured Rényi relative entropy. And this is not good for several reasons. For one that there's no like proper closed formula, you can't really compute this again, which was one reason why we went through the whole hockey stick divergence, etc., was that we wanted like an easier way to handle these quantities. And the measured relative entropy is not really like the quantity that we would like for that. And the other thing is also that this quantity is not additive. So all these nice properties you have about composing different differentially private algorithms wouldn't hold that easily, or wouldn't really hold if you look at a measured relative entropy. Okay. But the good thing, of course, would be that for alpha going to infinity, it would just recover the standard version of epsilon differential privacy. So how do you actually want to do this? You, instead of using like the measured version of your Rényi relative entropy, you just take like one of the fully quantum definitions of Rényi divergence. Okay, I'll present this here in a lot of generality, so you can, I don't know if you ever read like any like paper or like Marco's book or something on like Rényi divergences, you know, there's like lots of them, right? There's like as many as you want to define, you can basically, but as long as like, I just want to look at them for now, like not making a particular choice, I just want them to obey like a certain set of properties. And for these, I listed some of them here, like additivity, data processing, and so on, because those are what really going to give us like nice properties of our differential privacy definition. Okay. Okay, I listed some here, like percentage of the Rényi divergence. But really just any of these divergences will do for now. And then how do you define Rényi differential privacy? Of course, you just take the supremum over neighboring states, and you want this to be smaller than epsilon. As long as you choose a Rényi divergence that in the limit of alpha to infinity gives you the max relative entropy, this will reduce to the standard definition of alpha to infinity. So what you get is kind of a new definition of differential privacy with two approximation parameters. But it's easier to achieve in differential privacy, but it does not have than epsilon differential privacy, but it does not have this downside of introducing this epsilon, the delta, this additive error parameter that comes with all its own problems. And so this is kind of our proposed fully quantum generalization of the Rényi differential privacy. And of course, now after defining this, one needs to check that this actually has all the nice properties of classical Rényi differential privacy in order for it to be as useful as the standard version. And the first one is, of course, to show that epsilon differential privacy should always imply this Rényi differential privacy. And this is actually quite easy to see because every Rényi divergence that fulfills this list of properties that I showed earlier is upper bounded by the max relative entropy. Okay, that's maybe not a completely trivial statement, but you can quite easily show this if you just look at some results of these quantities. And this means that an epsilon differentially private algorithm is also always epsilon alpha Rényi differentially private. So in some way, you already get one implication, and the other one is to show that this is actually like a still more stringent criteria than the epsilon delta differential privacy. And for that, we can have another property of this quantity, which is any epsilon alpha Rényi differentially private algorithm is actually also epsilon delta differentially private, just that the delta is now kind of a slightly more complicated function of epsilon and alpha. And again, this is just a property of like these divergences that you get like this implication, like always, whatever divergence you choose. Okay, so you can see from here kind of that the Rényi divergence or the Rényi differential privacy is sandwiched between the standard, like the original epsilon differential privacy, and this like weaker epsilon delta differential privacy. And okay, and this kind of mirrors what I said about the differential privacy earlier. Just by the properties of the divergences, you can get plenty of properties back. And like the post-processing, because they obey data processing, so of course you get post-processing. And also again, like composition theorem, where I combine two Rényi differentially algorithms. And here I briefly just want to point out one important thing, which actually motivates why in the classical setting people are so like why they really want to look at this Rényi differential privacy, which is if you looked at epsilon delta and you composed them, then you saw that the epsilons and the deltas, they just added up under composition, right? So maybe you still remember that from one of the earlier slides. But the important thing here is that the alpha does not add. So the alpha, which is like a parameter that kind of substitutes your delta, while the delta kept getting worse with every like composition, the alpha actually stays constant, which means like this undesirable approximation parameter that you add besides the epsilon, it doesn't get worse over time by composition, which is really like classically already was seen as a great improvement over the epsilon delta differential privacy. Like we talked about this a couple of times, right? The delta is a parameter that you want as small as possible. So if it like grows under composition, that's actually a very bad property. And here the alpha actually doesn't have this problem. The alpha stays constant. Okay, so our definition actually mirrors this. Okay, and I guess I'm running out of time. Just briefly to say that we kind of make a case why the sandwich Rényi divergence is actually the divergence you want to look at. And it's simply because it has many desirable properties that not all of these fulfill. And maybe just to briefly say the last two are maybe the most interesting ones or non-obvious ones, which is that they are one, the easiest to achieve. The percentage one is always the smallest of these divergences. And also, you can actually write this as a regularized, so I'm not going to go into too much detail, regularized measured relative entropy. So in some sense, you do still have this interpretation of measurements on your quantum systems, just that you need to look at like n copies of them. And that seems to be like a quantum kind of way of looking at things, that you can't just, you need to take into account correlations even in your measurements and so on if you want to see the optimal rates. This is maybe also something that can be explored further. We know actually like results for these measured things are not additive, so maybe there's also some kind of security implications of these, that if you would check it only on like if you would just check classical differential privacy on like the measurement outcomes, you're somewhat missing like the full quantum picture because you're not looking at these correlated measurements. Okay, and then in the interest of time, I'm just going to skip over the last hypothesis testing part, which basically just says we can rewrite that a differential privacy condition also in terms of hypothesis testing. And what this mostly gets us is a set of conditions on the typical type 1 and type 2 error probabilities in hypothesis testing. And I'll skip over a couple of things to not keep everyone here too long, but it allows us to do two things, which is one, it gives us very nice pictures of regions in which like differential privacy holds under certain conditions. And it actually also allows us to prove some new, like nice technical results, for example, relations between different privacy regions of differential privacy. So we can, for example, if we allow delta to be a bit bigger, we can get a smaller epsilon, and this allows us, or this lemma just tells us how much smaller we can choose epsilon if we allow for a slightly bigger delta. Anyway, I'm happy to answer more questions about this later, but I don't want to get too much over time. And then we can do, this is nice for like numerics, you can plot some nice pictures and stuff, where like more depolarizing noise pushes your outcomes of the algorithm into your private region. And then I just conclude with everything I said during the talk, like quantum generalizations, easier proofs for old results, some new properties and new bounds, and improved bounds for like specific noise models, and then generalized approaches to like things like Rényi differential privacy or local differential privacy. But I think that's it. Thanks for coming.